Hi, so this video is on RSA, first of 3 videos on RSA encryption scheme. And we're going to start in this video with an overview and some details, and then we'll realize that there are 2 crucial algorithms, and those we're going to call modular exponentiation and the extended GCD algorithm. So these will be the 3 videos. And you definitely should want to look at the document rsa.pdf at the course website. In the documents folder, it explains everything in gory detail, and many things that we're not going to mention in these notes. Okay, so RSA is a way to send a message securely, and it's called public key encryption, as we'll see. We'll see exactly what that means, and unlike perhaps in a security class, we're going to look at the algorithmic details. So, of course, what we're interested in is the algorithms. And the cool thing is that both the 2 that we use, in some sense, use divide and conquer. Technically, the GCD, is reduce and conquer. Some people make a distinction. Divide and conquer is when you kind of split the problem into 2 or 3 or 4 pieces and solve them separately. Reduce and conquer is where you recursively do simpler problems than the one you were originally given. But we'll see that both those being used. Okay, so here's how RSA works. So the RSA scheme is as follows. Step 1 is at headquarters, we get large primes, P and Q. So that's one of our big issues that we'll have to talk about later in this video, actually, on where do you come up with a giant prime number. And by large, we're talking, 300 digits, something of that ballpark. The larger they are, it's probably the more secure the method is. If you pick them to be 20 or 30 digits, it could certainly be broken by modern computers, or probably even 100. So that bar keeps going up as the computers get faster, but we'll claim that it's still secure. Okay, so step 2 is to form the number n, which is P times Q. And that's, of course, kind of cool that we just studied an algorithm that can do that somewhat more efficiently than we might think. But even if we weren't efficient and didn't do the Karatsuba that's into the 1.58, even the theta to the n squared wouldn't be bad. So if n ends up being 1,000 digits, this would only be like 1,000,000 steps in some sense, which could be done pretty easily. And this is kind of the public keys we're forming here. N is one of the public keys, we'll see. Okay, and oops. Then we also form, strangely, but we'll see exactly why later in this video, the quantity P minus 1 times Q minus 1. And we'll come back to that guy shortly. Then step 3 is we get a largish E, and what we need here is for the greatest common divisor of phi and E to equal 1. And we'll see what that allows us to do later. And we'll talk on the 3rd video about the GCD algorithm that can use that information. Okay, so that's it. So then we're all set to let people send us message. So we publish N and E, and we even say to send a message A, so A is just a number, so think of it as a 300-digit number. So you could take plain text and use ASCII codes of the symbols and chunk them all together to form one giant number. The only restriction is it has to be less than n for the math we're going to do later to work. So to send A, you compute or form A to the E n z sub n. And we call that C. So C is the computation A to the E and Z sub n. So doing that is our modular exponentiation that we'll talk about in detail in this second video. Okay, So that looks like an insanely difficult thing because you're taking a huge number A and raising it for a huge power and taking it at mod some other big number, but it looks like it would have an insane number of digits. But it turns out we can do it more efficiently than you might expect by using divide and conquer. Okay, so you publish that, so if someone wants to send E, they just compute this and send C off. Okay, so now we're ready to solve it. To decrypt it, we need to compute D such that D times E is equal to 1 in Z sub P, phi. Okay. And it's not at all obvious how to get through that, and you can't do it unless you know phi, of course. So it turns out this is from the GCD algorithm that we'll study in this third video on this topic. Okay, and then when someone sends us C, so we receive the encrypted message C, and we compute back at headquarters. So this is back at headquarters. Oh, this is all happening at headquarters actually, except for the sending of A. That's what someone in the outside world does. We just compute C to the D in Z sub n. So that's another one of these modular exponentiation operations, and it turns out that's equal to A. So that's all there is to it. So that's the general scheme. So okay, so why is this secure? Or is it secure? So it's widely believed by everyone doing algorithms that's willing to talk about it. Maybe they have some clever algorithm, incredibly clever algorithm or hardware or something tucked away in the NSA or in Russia somewhere or something that can factor. But we believe that the problem of factoring in and realizing that it's equal to P times Q, which could allow you to form phi, which is P minus 1 times Q minus 1. And as soon as you know P and Q, N is published, as soon as you know P and Q and by factoring, then you can get phi, which you can get D, as we'll see in the third video. And then you'd be able to, anybody who can factor, in other words, knows everything they know back at headquarters. At headquarters, they start with P and Q and compute N and phi. So there's no difficulty there. It's the unreversibility of unmultiplying these guys, factoring them, that's the basis for the security. Okay. Oh, and it's also for two people to communicate with RSA. This guy A publishes their N and E, and B uses that to send message to A that A can decrypt, and B has their N and E that they publish, and A can use that. So two-way communication is possible if both people publish, do their own RSA scheme. Of course, if they use the same one, then that would be bad. But it's very unlikely, depending on how we do the first step of finding P and Q. Okay, so it's time to look at some theory, which generally is scary, and I'll just comment that I'm going to leave this. You can read all about this if you want. I'm going to really it's not going to be on the test or really required. It gets into some pretty standard little number theory, abstract algebra things that would be really fun to do, but probably not our focus. Okay. So, before we head on to that, there's three things we apparently need. We need to be able to get a large prime. Get a large prime, need to be able to do modular exponentiation, and we need to be able to do the GCD, it turns out. So those are the three things, and in the rest of this video, we'll take care of the get a large prime. So it turns out, this is just a fact, that if you take 2 to the n minus 1 in z sub n, and you get 1, so we always write it like this. So the n z sub n just means you do arithmetic completely as usual, but every time you get a number bigger than n, you lop it back by taking out all the stray n's. So it's really just like we saw in the fast Fourier transform stuff. It's really a matter of treating n as 0, like clock arithmetic. So if you do this, then for a long time humans thought n is prime, but in fact that was proven when they got better at computing things, that all we can say is n is probably prime. And the probably is actually incredibly likely. So there are ways to check in polynomial time whether a given number is prime. So this scheme, it could actually be perfected. But for practical purposes, if we generate, like using the big integer class, and we use the get the probable prime, next probable prime method, we can rest secure in our beds at night that it is in fact a prime number. It's incredibly probabilistically, you'd have to be absurdly unlucky for it not to be a prime number. So, and the converse is, if p is prime, if n is prime, then 2 to the n minus 1 is equal to 1 in z sub n. So that's absolutely true. So it's like the converse of that is that if 2 to the n minus 1 equals 1 in z sub n, then it's prime. That's not quite true, but it's incredibly likely to be true. So we'll take it as sort of true. Okay, so from this one little fact, which I do prove in the notes in RSA, it's based on just analyzing how z sub n works. So here's why the scheme works. So we're assuming that we can get, and this is where we'll need to know how to do the GCD. So we'll get a k and d such that 1, which is going to be the greatest common divisor of phi and e, is actually equal to some number times phi plus d times e. So we'll learn in the greatest common divisor thing, we don't really care about getting the greatest common divisor. It has to be 1 for it to work. What we're interested in is this number here. Okay, so if that's true, and in fact we'll have to be careful, we need d greater than 0. And if d is greater than 0, since phi and e are positive, if d is positive, this is a positive number, and this is a positive number, so k has to be negative equivalently. That'll be important in a minute, so we don't get confused. So now, if we want to compute c to the d in z sub n, that's what we want to compute. But what is c? c is a to the e in z sub n, so we're actually computing a to the e to the d. Now I'm just going to put a big n z sub n off to the side here, because some of the things we're saying are true just because of algebra that works in ordinary numbers or in z sub n equally well, and some of them we won't be that careful with it. So the thing that's true for sure is if you've got a to e to the d, that's equal to a to the, that's a really basic fact of exponents. And then it's also true in general that ed, or de, because it's commutative, is equal to a, so we can say it's 1 minus k phi. But remember, k is negative, so that's actually 1 plus a number. And then it's also true in general that it's a to the 1 times a to the minus k phi. So a to the 1 is a, and what we want to prove is that in z sub n, this number is equal to 1. So that seems like, why would it be? But it's because phi was cunningly chosen. So let's look at a to the minus k phi. And, okay, that is in fact equal to a to the minus k, which is just a multiplied together minus k, because remember minus k is positive, because k is negative, raised to the phi. But then phi, if you recall, was weirdly taken as p minus 1 times q minus 1. Now we start to see why. So this we can write as a to the minus k to the q minus 1. So that quantity to the p minus 1. So this is just a number. So up here, I said something too weak here. This is actually true for any x. So if n is prime, then anything to the n minus 1 gives you 1 in z sub n. So this any number raised to p minus 1 will be equal to 1 in z sub p. And similarly, it'll be equal to 1 in z sub n, q separately. So in the two separate z sub p and z sub q worlds, this quantity is equal to 1, and it turns out it's pretty easy to see that that means it's also true in z sub n. That takes a little work, but that's the basic idea. All right, so the point is when you compute, backing up for a sec, when you compute c to the d and z sub n, that's a to the e to the d, and all this just says that it's equal to a times a number that turns out to be equal to 1, because phi has been carefully chosen so that this property, that a number to the n minus 1 is equal to 1 in z sub n, if n is prime, we apply it separately in the with prime p and prime q, and then we're leaving out the details of why that's true in the product, but it is true. So that's the end of this video. And the next one, we're going to look at modular exponentiation. And the following one, we'll look at the GCD, which is how the GCD is how we're going to get this fact. So that's an interesting algorithm in its own right. So thanks, and the next video we'll look at modular exponentiation.